Okay, so let's start. Let me start by sharing my screen and okay, so everybody, if you have not already done so, please go to my GitHub page, github.com muf148,
Sorry, I think
and
just
you
lost
will
your
see
audio.
two repositories on top, and go to the quantum machine learning with Qiskit 2.x, and from here, intro to primitives. Uh, you can run it either on Colab or VS Code. I'm going to be running it on a VS Code editor. Okay, so Gibran, my screen is visible.
Yes.
Okay, let me see if I can make the
Maybe
pointer.
zoom out a little bit. I think some of it might be getting cut off on the right hand. I'm not sure.
Okay, so okay. Hello. I think
Sorry, I
I
think
lost.
there was a brief disconnect on my part.
Okay, so let me start sharing the screen again. Okay, so is this better now, or should I
No, I think
zoom
it's
in?
good.
Okay, perfect. So what I'm going to do in this part is explain the use of Qiskit primitives for sampling and estimating. And I'm also going to show how you can run it on IBM Quantum Computer, even though in this workshop, I'm not going to do that. I'll have, the code is the same, and I'm going to describe it in this part, and then in the later sessions, we'll just be simply omitting this because to run synchronously with you, I'll have to run it on a simulator. Anyway, so if you have an account on IBM Quantum Computer, you can copy your token here and your API key over here, and you can name it the way you want, and then run this part, and this will save the credentials on your computer. And once you have this credentials saved, you can load your account by giving the name here, and then IBM servers, this variable will have this credential. And I'm using, for example, here IBM Torino, but you can use the other quantum computer as well. However, we are not going to be using this in this part of the lecture. This workshop will mainly run on two simulators. So one simulator that we will be using is this air simulator, which we can import from Qiskit Air, and you will have to install Qiskit Air on your either Colab if you're using that, or VS Code environment that you have set up. And once we have this air simulator and it's instant created as backend air, we can now set up uh, a sampler by importing it from the Qiskit IBM runtime. Sampler v2 is this version 2 of the sampler. And in the sampler, we have to specify the mode. So if the mode is air simulator, then this will sampler will work as the simulator. If the mode is IBM quantum computer, it will work as the work on the IBM hardware. So the syntax for running a simulator or IBM computer is almost the same. There are very few changes that you have to make. So the files that I'm going to be uploading, they can work on simulator and IBM computer both. So I didn't run this part, so let me run this. All right, so if we run this, okay. Now I'm going to be using two toy circuits just to show the use of basic primitives. So here is this simple circuit with just a Hadamard gate, and there are two classical registers that you see. There is this C register that is created when I specify classical bit 1 here. And then there is this MEAS classical register that is created when I use the command measure all over here. And I'm just using it to show that this, naming is important. Otherwise, if you don't use measure all, you just use measure, this result is stored in C and there are no two registers. And if you don't use one here, there will be only one register MEAS. So anyway, you run the circuit, and then we can also create parametric circuit very easily in Qiskit to run them to construct our own custom variational circuits. For this, we need to use parameter. We need to import parameter from Qiskit circuits. And if you want, you can, construct your circuits using quantum register and classical register like here and give them the names that you want. And in that case, when we measure, the results are not stored in C register, they are stored in whatever classical register we have used. For example, in creating this quantum circuit, you see I use QR and CR. QR is the quantum register and the CR is the classical register that I defined here. So CR is the name GSS. So the results are going to be stored on this GSS classical register. It's a simple circuit with two gates. They both have parameter theta and phi. And this parametric circuit, we can, use this template to build more complex parametric circuits as well. And since we use parameters, we need to know the order of the parameters, because once we specify the parameters later on, we will specify in this order. So it means in this circuit, parameter phi is coming first and parameter theta is coming later. And here I have a list of parameters, and you can see it's a list of lists. So this list has four elements, and each element has these two parameters. Two parameters because there are parameter phi and theta. So first value corresponds to phi, and second value correspond to theta. And before running it on the any backend, either the IBM quantum computer or air simulator, we have to transpile it so that all the elements in the circuit, they are transpiled to the language of the circuit. So let's run this array circuit, and then this is the transpiled circuit that I'm just drawing again. And if you want to run it on IBM quantum computer, you will have to transpile it according to the IBM quantum computer. So both of now these circuits are transpiled for the air simulator. So you see I have now changed their name to QC2 air. Similarly, for running an IBM quantum computer, we have to transpile, and you see that after transpilation, the circuit is mapped to one of the qubit on the quantum computer, because there are 133 qubits on quantum computer, and the transpiler chooses the best qubit to run your circuit. And this circuit is mapped to qubit number 37. The other circuit, and you see that the Hadamard gate that we had in the circuit is not showing here, because it's transpiled into the native gates of the IBM quantum computer, which are RZ and X square root. Similarly, the other circuit, we can transpile it for the desired quantum computer. And once it's transpiled, we can see the circuit to the qubits that it has been mapped to. It's mapped to qubit 29 and 36. And you see that they are not even, numbered adjacently. Because these are the two qubits that there might be a connection existing between them. The control X circuit is easy to implement. So that's why the transpiler mapped to these two qubits. Now, this is the basic layout of running the primitive unified blocks. And let me see, there's a question chat perhaps. So somebody is asking why SSE and GSS. So in LUMS, we have a School of Science and Engineering, and we also have a Grumani School of Social Sciences. So that's why I just, chose those two names. And can't get the reason why H is being transpiled into other gates, because the Hadamard cannot be implemented directly on the IBM quantum computer. So it has to be transpiled to the gates that the IBM quantum computer can implement. And depending on the quantum computer, the transpiled circuit will always look different, because different quantum computers nowadays, they have a different set of gates that they can implement on their hardware. All right. So this is actually the basic way of running uh, primitive commands on the simulator or on the IBM hardware. So we use the dot run method, and in the after dot run, we supply the pubs. So this is the first block, and the block has the transpiled circuit and the list of parameters. And since QC1 was the circuit with no parameter, you see I have written none, and then it needs the number of shots. So 100 is the number of shots that I'm going to be using. And the second block has another circuit and a list of parameters, which we call angles, and then the number of shots as 1000. And once we run it, the job is run, and all the information about the job is stored in job, this variable on the left, and then we can get the results out of it using the dot result method. Similarly, if you run it on an IBM quantum computer, the syntax would exactly be the same. You see, I have this syntax over here, and I have commented here. There's only one thing, that when you submit an IBM quantum computer, you might have to wait. Anyway, to access the results, we have to specify two things. Number one, that which pub are we accessing? Are we accessing the first pub, this one, which is index 0, or we are accessing the results of the second pub, which is indexed 1? So its index goes here, 0 or 1, and then there are 4 list of parameters. So that goes here. So either 0 or 1 or 2 or 3. And once we have the results, we can, plot it here. So similarly, for the second pub, so the second pub you see gave the error. The reason is that the second circuit, the second pub is QCT circuit, and it does not have MES gate. It has GSS gate, classical register in it. So we need to specify the classical register over here. Whatever the classical register in the circuit is here, it should be coming here. All right. So similarly, there's another example. You see there's a .gss already written here. So you have to be careful about this classical register whenever you get the counts out. So this is how we can run the counts out. Now, the second primitive that I want to introduce is the primitive to measure the expectation values. And for the expectation values, we have to specify the observables. And for that, we can use Pauli operator from the quantum information package in Qiskit. And then we can specify the observable. For example, this observable list has two observables. There is this observable XX with the amplitude 1, and then there is this observable ZZ with amplitude 1. We can have observable as some of these terms as well, and with amplitude anything that we want, as long as the amplitudes are reals. So we have a list of observables. So there are two observables. And if you want to run it on simulator, you can use it directly. But if you want to run it on quantum computer, you have to change the layout, because you see these are two observable. We have to tell the quantum computer that what are the qubits where these observable have to be transformed. So for that, we use the layout of the circuit for which we have to implement, and then we apply the layout with dot apply layout. So with this, you see the observables are mapped accordingly, because there are 133 qubits. So there is one observable here, X, and then another X here, because our circuits is mapped to these two qubits. Similarly, there's a Z observable here and Z observable here for the second observable. So this observable list has to be mapped. So once we do this, we can use the estimator variant 2 primitive from the IBM runtime. And then we have to tell it that what mode to use, either the air simulator or to use the IBM quantum computer, and prepare the instance of the estimator as estimator air and estimator IBM. Now, once we have done this, then we can run this primitive using dot run method, just like the sampler primitive. However, we now have to specify 4 inputs. Number one is the circuit. The second is the observable list. The third is the list of parameters. And the last is the tolerance in the expectation values. We have to specify that how good expectation value we want, because that will directly tell the algorithm how many times to run the circuit, and it actually computes it as 1 over tolerance square root. For example, if tolerance is specified as 0.005, the circuit will run 40,000 times, and after 40,000 times it will compute the average of the eigenvalues. And once we have the average of the eigenvalues, we can output the expectation values, the whole list, by just giving the index of the pub here and using the method dot evs expectation values. And you see, once we run it, we have a list of expectation values. The first list corresponds to the first observable. The second list corresponds to the second observable. And for each observable, we have 4 set of parameters. So this is the value for the first set, the second set, and so on. So the nice thing about this primitive run is that we can compute expectation values for a range of parameters in one go. We don't have to send in the list of parameters one by one. And that's going to be really handy when we will be implementing the quantum machine learning models. All right, so we can also check the standard deviations in the results, and you can see the standard deviations are within the tolerance limit that we specified. We specified 0.005, and it's able to get the expectation value within an error bound of 0.005. So this is one way of computing the expectation values. Air simulator is actually very useful and very widely used as a simulator because it can allow us to input noise models. We can do mid-circuit measurements. We can use, fake backends and so on. But many times, we only need just the expectation values, and that can be done in a simpler way using the state vector sampler and state vector estimator as well. So they are not in IBM runtime, but they are part of Qiskit primitives. So let's see how to use the state vector estimator and sampler. For them, let's import them and create their instance. And you see, I didn't have to specify the mode. Just like in Air Simulator, I had to specify the mode because there the mode could be IBM quantum computer or the mode could be simulator. But here, there's only one possibility that these can only be used for simulation purposes. So we don't have to specify anything. They are by default simulators. And once we have the instance of simulator, we can actually use exactly the same method. So with dot run SV sampler, I can sample the circuit again, circuit and angles and the shorts, and we don't even have to transpile the circuit. And similarly, for the second pub, we have the circuit, the list of arrays, and the number of shots. And once we have run the results, I can actually compare the results of the state vector sampler with the air sampler, and you see the results are almost the same. This little bit difference that you see, it's because at the end of the output, both simulator use pseudo random number generators. So because of those pseudo random number generators, there's a slight difference in the outputs of the two simulators. We can similarly use state vector estimator, but there's one key difference, and that is that we can't have measurements at the end of the circuits. So I have to redraw the circuits, and it's important because if you use the circuit with measurements in a state vector estimator, it will give errors. So I redo the circuits, and in my initialization of the circuit, I didn't specify any classical bits and I didn't put any measurements at the end. So that's important for state vector estimator. And once we have the circuit, we can compute the expectation values exactly the same way as the air simulator with .run method, we can specify the circuit, observable list, list of arrays angle, and the tolerance in the expectation values. And we can extract the expectation values using .evs method just as before. So let's run it. And if you want, you can compare the expectation values from both the air simulator and the state vector simulator. And for example, for the index, parameter index, like we had 0, 1, 2, and 3 parameters. So you can see that the state vector xx and the air xx, they are almost the same, and state vector zz and state vector air zz, they have the same expectation values. So this is uh, the way to run three basic primitives on Qiskit, and we are mostly going to be using state vector simulator in this workshop. So before the next lecture tomorrow, please go through this file and become comfortable with the state vector uh, estimator, uh, if nothing else. So with this, let's see if there are any questions.
Thank you, Faryad. No, there are no additional questions at the moment. Oh.
Just a quick confirmation that what we are doing is to make the parameterized circuit with X parameter to feature map and theta to ansatz, and the choice of X and theta would be determined by the model such that the result is the probability of occurrence of particular data. If 111 is pointing to something, then X and then data are chosen. So what I get from this, yes, so based on the model that we just discussed in the lecture before, you can approximately say that that's how we do, but sometimes we mix the x and theta as well together, and sometimes there's no theta. We are only just doing a feature map because we are using it as a higher dimensional uh, space transformation instead of as a parametric circuits. So, and those methods are called kernel methods, and we'll be spending the last day on the kernel methods where we don't have any, explicit parameters, even though we can include parameters in that as well, where we want to align our kernel with something that we are trying to do. And thank you to everyone who